Hey class! Today we're going to start the last section and we're going to talk about polar bonds today. So first we kind of have to go over what is polar and versus nonpolar. So we know that covalent bonds is whenever electrons share atoms between them. Now the way they share them can differ. They can share them equally or they can share them unequally. And this is going to depend on the kind of atoms that are involved and how many are going to be bonded together. These determine certain molecular properties. So today we're going to talk about polar versus nonpolar, and a specific property that comes to mind is solubility. How easily does things dissolve in water? And that's going to be dependent on, is it polar or nonpolar? So let's kind of talk about this electron sharing. Here is a good analogy of it. I have two atoms. So here's one atom. Here's another atom. Also, I'll put two there. And they're sharing these two electrons between them. Kind of like during tug of war, you have two groups. So this group of students over here is one atom, and this group over here is another one. And the rope in the middle are your pair of electrons that they're sharing. They're going to pull. One team might be stronger than another, so they might pull the rope closer towards them. Or maybe the teams are equally in strength, so the rope stays in the middle. So when atoms in a bond pull equally, usually this occurs whenever the atoms are identical to one another, our electrons are shared equally and therefore the bond is considered to be nonpolar. On the other hand, a polar covalent bond is one in which the electrons are shared unequally. That just means that one atom is stronger than the other in terms of pulling electrons. And this comes down to a certain characteristic that we learned when we were talking about trends in our periodic table, and that is electronegativity. The electronegativity value is going to depend on which atom is going to want those electrons more. So again, remember electronegativity was defined as the ability of an atom, whenever it's in a compound, to attract electrons. Here is our electronegativity value table that's given in your notes. You'll be given this on your test. There is one value that's not included here that I want you to add, and that is xenon, so Xe, has an electronegativity value of 2.6. So I want you to add that into your notes. We can look at these electronegativity values and hopefully see that fluorine has the highest electronegativity value. So fluorine really wants those electrons. Whereas everything over here on the left-hand side, like cesium, it doesn't have a high electronegativity value. And while we're reviewing, let's kind of go over our trend. Remember, electronegativity value is going to be highest at the top of a group, and it's going to be the highest all the way to the right side of a period. So the far right corner is the highest, the left bottom corner is your lowest. Now, because we have electronegativity differences, this is going to affect slightly the charge. The more electronegative atom is going to have those electrons closer to it, so it gets a slight negative charge, whereas the other atom does not want those electrons as much, so they're farther away from them. They actually get a slight positive charge. Yep. The higher the electronegativity value, the greater those electrons are going to want to be by it. So if we look at two elements, hydrogen and chlorine, hydrogen has an electronegativity value of 2.1, whereas chlorine has an electronegativity value of 3. These values are quite different from one another. So if hydrogen and chlorine would come together to form a compound, those electrons are going to be closer to our chlorine. So chlorine will have a higher electronegativity value and get a slightly negative charge, and hydrogen will have a lower electronegativity value, so it gets a slight positive charge. And the way we denote these slight positive and negative charges is through the Greek letter delta, and it's the lowercase version. So it looks like a little O with a stem on top. Here, this just denotes that hydrogen is slightly positive and chlorine is slightly negative. Another way we can denote partial charges is by using our electron cloud diagram, and this just shows our electron density. You're going to have more dense region closer to your most electronegative atom. The last way, besides just using our delta sign and our electron cloud model, is to use an arrow pointing towards your most electronegative atom. If you're looking down here with hydrogen and chlorine, the arrow is going to point towards chlorine because that's where those electrons are going to want to go. So besides those two, let's kind of look at water. Water is an extremely polar molecule, and it's used to dissolve a lot of salts because of its polarity. So it is, if we look at this, oxygen, if you look on your table, is a 3 on that scale. Hydrogen is a 2.1, I believe. So oxygen's a 3.5. Hydrogen's a 2.1. 3.5. If you look at that, there's a big difference. Oxygen has the higher value, so it's going to have a bigger electronegativity. Hydrogen's going to have the lower electronegativity. That means oxygen's going to be negative and hydrogen's going to be positive. So oxygen negative, hydrogen's positive. Now, in terms of this, the electronegativity difference between the two atoms will tell you what kind of bond is likely to form. It's not 100% foolproof because these lines are a little bit blurred, but it does give you a good representation or idea. One thing to fix in your guys' notes is here in your notes, it said 0.4, and down here, this one also said 0.4. But in order to kind of denote a difference there, I want you to change this to 0.41. I also want you to change this value to 1.01 and this one to be 1.99. And that just makes clear distinctions for your homework, so you guys don't have to worry about which category does it fall under. So the way we find electronegative difference is subtract, because that's how we find the difference of things. So we would find the value for one atom and the value for the other, and then subtract those two. So if you're looking at your chart, you should be able to answer this and then look at this table and find out. So there is no sharp boundary between ionic and covalent bonds. If we look at this, as the electronegativity difference increases, the more polar that molecule is going to be, because one of those atoms are going to pull those electrons more strongly. If the difference is so extreme or above 2, these electrons are going to be stripped and pulled away completely, and that's when we get our ionic bond. They are no longer sharing. One of them just steals it completely. So here we're going to identify what type of bond is going to form between two different types of atoms or the same atom. And we're going to classify it as being nonpolar covalent, moderately polar, very polar, or ionic. So this is where you're going to have to get out that little table and put your values down. So here I'm going to write down these values, and we're going to flip back and look at the table and be able to figure out our difference. So our atoms that we have to look up values for is nitrogen, hydrogen, fluorine, calcium, aluminum, and chlorine. So let's go back and look at this table. Nitrogen, we're going to see, has a value of 3. Hydrogen is still 2.1. Fluorine is 4. Calcium, it's a metal, so it's going to have low. It's going to be 1. Aluminum is 1.5. And chlorine is going to be 3. Now that we're back here, if we look at this, we saw that nitrogen was 3 and hydrogen was 2.1. When you subtract this, this gets me a difference of 0.9. 0.9 from our table tells me that this value is going to be moderately polar. So moderately polar covalent. Here, fluorine and fluorine, both of them are going to have a charge. So when I subtract it, my difference is 0. This tells me if I look at my chart, my difference is 0. It's going to be nonpolar. Calcium has an electronegativity difference of 1. Chlorine is going to be 3. So when you subtract these, you get a -2. But we just have to worry about it being 2. So if it is 2, if you look at your chart, 2 or greater is going to be ionic. And the last one is aluminum. Your value is 1.5. Chlorine, your value is 3. So when you get the difference, that's a difference of 1.5. If you look at your table, that is very polar covalent. So very polar covalent. This chart works really well, and just subtracting the differences works well whenever you're working with two atoms or just trying to find a specific bond. However, the presence of a polar bond doesn't mean that the entire molecule as a whole is polar, especially when you're working with atoms that have 3, 4, or 5 atoms. So a polar molecule is whenever the entire molecule is polar. So part of it is positive and part of it is negative. Here are polar versus nonpolar rules. You don't have these in your notes, but I want you to take out your little sheet that tells you the electron geometry, bonding groups, electron geometry, and your bond angles, and write this on the back because you will get to use these rules on your test. So make sure you flip that over and write down these rules. Now, oftentimes, if you do see a polar bond, the whole entire molecule will be polar. And that means, again, we have these different charges. We have a slightly positive and a slightly negative. And these two electrically charged regions are called poles, and we like to call them dipole moments. So for hydrogen and chlorine, our dipole moment is hydrogen, again, is slightly positive, and chlorine is slightly negative. The reason I gave you the rules, though, is there might be a polar bond there, but the molecule as a whole is nonpolar, and that's because polarity of an entire molecule depends on its shape and its orientation. So that's why we've been learning shapes before we've gotten into this. Carbon dioxide has a polar bond. There's a difference between carbon and oxygen, but because the shape is linear, this is said to be nonpolar. Whereas water, it has polar bonds, but because its shape is bent instead of linear, this entire molecule is going to be considered polar. So that's the end of today's lesson. We're going to do these examples in class tomorrow to kind of give you help with the rules, and then you guys will get an assignment. Let me know if you have any questions, and I hope you have a good day.